Picture the night sky. It is a canvas of quiet, twinkling lights, each one a story, a sun like our own. But what if I told you that some of those lights are not one star at all, but 6? Nestled in the vastness of space, there exist extraordinary stellar families so complex and rare that they defy our very understanding of how stars live and interact. These are sextuple star systems, cosmic configurations where 6 stars are locked in an intricate gravitational dance, a celestial ballet governed by laws that push the boundaries of physics and imagination. For centuries, we gazed up and saw simple binaries or triple systems, but the discovery of systems with 6 stars challenges everything we thought we knew about stability, formation, and the sheer possibility of such arrangements in our universe. What makes these systems so captivating isn't just their rarity, it's the sheer strangeness that emerges from their existence. Imagine the sky from a hypothetical planet within one of these systems, multiple suns of different colors and sizes rising and setting in a clockwork of orbits within orbits, creating days without nights, shadows pointing in 3 directions at once, and seasons dictated by a complex interplay of gravitational tides and stellar winds. These are not calm, orderly systems. They are dynamic, chaotic, and brimming with phenomena that seem almost fictional. Stars eclipsing one another in rhythmic precision, violent flares triggered by tidal interactions, and runaway stars ejected from gravitational slingshots. They represent some of the most extreme laboratories nature has to offer, places where the rules are rewritten and the unexpected becomes ordinary. In this video, we're going to explore 30 of the most incredible, bizarre, and astonishing discoveries about these sextuple star systems. From how they manage to not tear themselves apart to the mind-bending ways they influence planets, dust clouds, and even time itself, each revelation pulls back the curtain on a deeper layer of cosmic mystery. You'll come away not just with facts, but with a sense of wonder at how much strangeness the universe holds, and how each discovery brings us closer to understanding not only the stars above, but the very fabric of reality. So let's begin this journey into one of astronomy's most thrilling frontiers. Our journey into the strangeness begins not with a recent revelation, but with a star we've known for millennia, Castor, the second brightest star in the constellation Gemini. For most of human history, it appeared as a single, unassuming point of light. But in 1719, the astronomer James Bradley made a curious observation: Castor wasn't alone. His early telescopic work suggested a companion, making it one of the first binary stars ever identified. This was the first hint that our cosmic neighborhood was far more social than we ever imagined, but the true depth of its complexity would take over a century to fully unravel. The next major breakthrough came in 1904 when spectroscopy revealed something astonishing. Each of the 2 stars visible through a telescope was not a single star at all, but a spectroscopic binary, a pair of stars so close together that they couldn't be resolved by any telescope of the era. Their orbital dance was revealed only by the Doppler shift of their combined light, their spectral lines wobbling as they circled one another. Suddenly, Castor was not a binary, but a system of 4 stars organized into 2 tight pairs. Astronomers were stunned. A quadruple system was already a rarity, a cosmic oddity that challenged conventional formation theories, yet the story was still incomplete. The true sextuple nature of Castor remained hidden for another several decades. The final piece of the puzzle was a faint, distant speck of light designated Y Geminorum, often called Castor C. Initially thought to be merely a distant background star or a simple companion, persistent observation revealed its true nature. This faint point was itself an eclipsing binary, a pair of red dwarf stars that orbit so closely they periodically pass in front of each other from our viewpoint, causing a detectable dip in their combined brightness. Most crucially, this pair was gravitationally bound to the 2 brighter binary pairs, completing the intricate 6-star system. So, after 165 years of persistent discovery, the full picture emerged. Castor is not a single entity but a complex hierarchy of three binary pairs. The two bright pairs, Castor A and Castor B, orbit each other over a period of several centuries. Much farther out, taking thousands of years to complete a single orbit around the inner quartet, is the dim red dwarf pair Castor C. This layered structure, a binary of binaries, was the first confirmed proof that nature could build and maintain stellar systems of such breathtaking complexity and sheer gravitational ingenuity. It shattered the ceiling of what we believed was possible, proving that our universe has a flair for architectural drama on a scale we had only just begun to appreciate. Now, if the simple structure of Castor seems complex, prepare to have your mind stretched even further. The gravitational dance in a sextuple system is not a stately waltz. It's more like a mosh pit with 6 participants, each pulling and pushing the others in a chaotic, unpredictable frenzy. With so many massive bodies in such a relatively small space, the delicate gravitational balance required for long-term stability is almost impossible to maintain. These systems are fundamentally chaotic, operating on the razor's edge of cosmic disaster, where even the smallest perturbation can send the entire intricate arrangement spiraling into a new, violent configuration. The core of this instability lies in a concept known as the n-body problem. While we can perfectly calculate the stable, elliptical orbits of two stars around each other, the moment you introduce a third, fourth, fifth, and sixth star, the mathematics becomes fiendishly complex and ultimately unsolvable in a predictable, long-term way. The gravitational influences from all the other stars constantly tug on each orbit, introducing tiny changes that compound over centuries and millennia. These minute perturbations mean that predicting the exact position of any single star far into the future is a fool's errand. The system's fate is governed by chaos theory, where the flap of a butterfly's wings could, in a cosmic sense, eventually trigger a stellar collision. This chaotic environment leads to some of the most dramatic phenomena astronomers can observe. Stars can be gravitationally slingshotted, flung out of the system entirely at incredible speeds to become hypervelocity runaway stars, forever destined to wander the void between galaxies. In other scenarios, the orbits of two stars can decay, drawing them closer and closer until a catastrophic merger occurs. This isn't a gentle blending. It's a violent, explosive event that can create a brand new, more massive star or even trigger a spectacular stellar explosion known as a red nova, briefly outshining entire galaxies. Perhaps the most fascinating and counterintuitive outcome is the potential for a temporary truce within the chaos. Through a series of complex gravitational interactions, a few of the stars can sometimes be ejected, not from the entire system but from their immediate group. This can leave behind a simpler, more stable system, like a tight quadruple or a binary, while the ejected stars form a much wider, looser orbit around them. It's as if the system, in a desperate bid for survival, simplifies its own structure, booting out the troublemakers to achieve a more peaceful equilibrium. This makes every sextuple system we find a cosmic time bomb, a snapshot of a fleeting moment in a billion-year drama that could end in separation, collision, or a brilliant, fiery cataclysm. But of course, the universe always has a way of showing us that even our wildest theoretical models can be outdone by reality. For decades, Castor stood as the singular, classic example of a sextuple system. Then, in 2021, an automated sky survey designed to hunt for planets delivered a curveball that would redefine the field. The Transiting Exoplanet Survey Satellite, or TESS, was scanning the sky when it flagged an unassuming star with a catalog number, TIC 168789840. The data it returned wasn't just unusual, it was unlike anything astronomers had ever seen. The light curve, the graph of the star's brightness over time, was a chaotic mess of dips and peaks, a frantic, scribbled signature that seemed to defy all explanation. After months of meticulous analysis, the truth emerged, and it was staggering. This wasn't a single star behaving strangely. TESS had stumbled upon the first known sextuple system where all three pairs of stars are eclipsing binaries. This is an almost impossibly rare geometric alignment. It means that from our precise vantage point on Earth, we are looking almost directly down onto the orbital planes of all three binary pairs. As each pair of stars circles one another, they periodically pass in front of their partner, blocking a fraction of its light and creating a distinct, measurable dip in brightness. The result is a complex symphony of eclipses, an overlapping series of signals that creates that incredibly complex light curve. This unique alignment transforms TIC 168789840 from a mere curiosity into the most precise astrophysical laboratory we have for studying these systems. Each eclipse is a treasure trove of data. The depth of a dip reveals the relative sizes of the stars. The timing between eclipses gives us their orbital periods with incredible accuracy. And by combining the light from all these eclipses, astronomers can perform a technique called spectrophotometry, essentially disentangling the individual light signatures of all 6 stars to determine their masses, temperatures, and even their compositions. It's like having a detailed instruction manual for the entire system, allowing us to reverse engineer its formation and predict its future with a level of precision that was previously unimaginable. The system itself is a fascinating hierarchical arrangement. At its heart is a relatively tight trio, a central binary pair that whips around each other in just over a day, orbited by a third star every 8 days, forming a compact triple system. This inner trio is then locked in a gravitational dance with 2 other, more distant binary pairs that orbit the center of mass over much longer timescales. This layered structure provides crucial clues, suggesting the entire system likely formed from a single, unusually massive and turbulent cloud of gas and dust that fragmented in a very specific cascading manner. The gift of its perfect eclipsing geometry means we are not just seeing 6 stars, we are measuring them, weighing them, and taking their temperature, unlocking the deepest secrets of stellar multiplicity one eclipse at a time. While the gravitational chaos of these systems is a spectacle in itself, the stellar personalities involved create an equally dramatic show. A breathtaking diversity of type, color, and temperament all coexisting within one family. In most star systems, members are relatively similar, having formed from the same cloud of material, but sextuple systems throw that convention out the window. Here, you can find the entire stellar spectrum living under one cosmic roof, from faint, cool red dwarfs that smolder for trillions of years to immense, scorching blue giants that live fast and die young in spectacular supernova. This extreme variation isn't just a curiosity. It creates a thermal environment of such stark contrasts that it defies comparison to anything else in the galaxy. Imagine standing on a hypothetical planet nestled within such a system. Your sky might be dominated by a brilliant blue-white star, its intense ultraviolet radiation bathing the landscape and heating the surface to extreme temperatures. But look across the heavens and you might also see a deep red sun, a far cooler object providing a gentler, warmer glow. The climate on this world wouldn't be dictated by a single cycle of day and night, but by a chaotic symphony of heating and cooling as these different stars rose, set, and eclipsed one another. The temperature could swing hundreds of degrees in a matter of hours, creating impossibly violent weather patterns and a surface environment that will be constantly shifting between a blazing furnace and a deep freeze. This thermal pandemonium originates from the way these systems form. A single, massive cloud of gas and dust begins to collapse, but the immense gravitational forces at play cause it to fragment unevenly. Some pockets condense into dense, hot cores that ignite as massive O-type or B-type stars, burning at surface temperatures exceeding 30,000 degrees Celsius. Other fragments might be smaller and slower to coalesce, eventually becoming low-mass M-type red dwarfs that barely reach 3,000 degrees. Because all this happens in relatively close proximity, these wildly different stars become gravitationally bound from birth, locking their extreme differences into a permanent, intimate relationship. The consequences of this thermal inequality are profound and actively shape the system's evolution. The most massive, hottest stars produce fierce stellar winds, a relentless outflow of high-energy particles. When these winds slam into the gentler winds from a cooler companion star, it creates shock fronts that heat interstellar material to millions of degrees, generating intense X-ray emissions that can be detected across vast distances. Furthermore, the ultraviolet flux from a hot giant can literally boil away the outer atmospheres of its cooler siblings, a process called Roche-Lobe overflow, stripping them of material and fundamentally altering their lifespan and ultimate fate. This constant radiative assault also dictates the conditions for planet formation. The protoplanetary disks of dust and gas that swirl around young stars are at the mercy of their brilliant neighbors. The intense heat from a nearby blue giant can evaporate these disks prematurely, preventing planets from ever forming or shredding them down to barren, rocky cores. It creates a cosmic real estate market where the only potentially habitable zones are not just around a star, but in incredibly specific and dynamically shifting pockets of space, far enough from the blue giants to avoid sterilization but close enough to a red dwarf to capture enough warmth. It is an environment of extreme and paradoxical beauty, where fire and ice don't just coexist, they are locked in a perpetual gravitational embrace. This layered structure, often called a hierarchical system, is the universe's ingenious solution to keeping 6 stars from immediately tearing each other apart. It functions like a set of gravitational Russian dolls, a complex nesting of orbits within orbits that imposes a fragile order on the inherent chaos. The most common configuration we see is 3 binary pairs, but these pairs don't just float independently, they are themselves organized into 2 larger pairs. Imagine 2 tight duos of dancers, each pair spinning rapidly on their own, while simultaneously circling each other slowly as a group. Then, the 3rd binary pair orbits this entire central quartet from an even greater distance, completing a grand, slow dance that can take thousands or even tens of thousands of years. This arrangement is crucial for stability. The gravitational forces are strongest within the tightest binary pairs, binding those 2 stars together incredibly tightly. The force between the 2 inner pairs is weaker but still strong enough to keep them orbiting a common center of mass. The gravitational link to the outermost binary is the most tenuous of all, a gentle tether that is easily influenced by external forces. This hierarchy effectively compartmentalizes the chaos, localizing the most violent gravitational interactions to the smallest scales and preventing the entire system from destabilizing all at once. It's a brilliant natural engineering feat that allows these complex families to persist for billions of years. Yet, this very structure presents a monumental challenge to our theories of how stars are born. The standard model suggests stars form from the collapse of a single, rotating cloud of gas and dust. For a binary system, we can imagine that cloud fragmenting into 2 cores. For a triple, perhaps a smaller piece breaks off, but to form a sextuple system, the initial cloud must undergo a precise, multi-stage fragmentation process that is incredibly difficult to simulate and even harder to explain. The cloud must fragment first into 2 or 3 large clumps, but then each of those clumps must itself fragment again into binary pairs, all while the entire system remains gravitationally bound. This requires specific conditions of temperature, density, and turbulence that are exceptionally rare in the cosmos. The greatest mystery this hierarchy creates is the question of long-term survival. Over cosmic timescales, the gravitational influences from other stars, passing gas clouds, and even the subtle effects of general relativity act like tiny, constant tugs on this delicate arrangement. The system's stability is a careful balancing act, and a significant perturbation could cause the outermost binary pair to be stripped away entirely, leaving behind a stable quadruple system. Alternatively, interactions could destabilize the inner orbits, leading to a violent merger or ejection. Every sextuple system we observe is therefore a cosmic snapshot, a fleeting moment in a billion-year drama. It might be a temporarily stable configuration on its way to a simpler state, or it could be a rare survivor that has somehow maintained its intricate dance since the dawn of time, a living relic of the turbulent conditions in the early universe. If you thought forming a planet around a single star was a delicate process, try imagining that cradle of creation being constantly kicked and jostled by the gravitational pull of 5 other suns. For the longest time, astronomers believed the violent, chaotic environment of a multiple star system would be a planetary dead zone, a place where the gentle accretion of dust and rock needed to build worlds would be perpetually disrupted. The discovery that planets can and do form in sextuple systems is perhaps one of the most profound and unexpected revelations in all of modern astronomy, forcing a complete rewrite of the rules on where we might find habitable real estate in the cosmos. The journey of a planet here begins within a protoplanetary disk, a flat, spinning ring of gas and dust that encircles a young star. In a calm, solitary system, this disk can rotate peacefully for millions of years, allowing dust grains to gently collide, stick together, and eventually snowball into planetesimals and full-fledged planets. But place that same disk within the gravitational turmoil of a sextuple system, and it enters a cosmic battlefield. The gravitational tides from the other 5 stars act like immense, invisible hands, constantly squeezing, stretching, and warping the disk. This relentless perturbation can truncate the disk, sharply cutting off its outer edge and limiting the amount of material available for planet formation. In the most extreme cases, these forces can rip the disk apart entirely, scattering its precious planetary building blocks into the void. Yet against all odds, some disks persist. They don't just survive, they are sculpted by the chaos. The same gravitational forces that can destroy also create opportunities. They can trigger density waves within the disk, ripples that act as cosmic construction zones, forcing material to pile up and accelerating the process of planet formation. It's a high-risk, high-reward scenario. While many potential planets are likely torn apart or ejected, those that do manage to form are forged in a crucible of extreme physics, emerging as some of the most exotic and fascinating worlds we can conceive. Picture the view from the surface of such a planet. Your sky would not feature one sun, but 6. Some would be brilliant pinpoints of light, while others might appear as distant, glowing orbs. The concept of a day would be almost meaningless, as these stars rose and set in a complex, multi-rhythmic ballet. You might experience periods of near-constant daylight from multiple sources, followed by a brief, profound darkness when all 6 are below the horizon. The light itself would be a bizarre blend of colors, the harsh blue-white glare of a massive star, mixing with the deep crimson glow of a red dwarf, casting strange, multi-hued shadows across the landscape. The seasons would be a spectacle of unimaginable complexity. They wouldn't be dictated by a simple axial tilt, but by the ever-changing distances and positions of the 6 stars in their long-period orbits. You could have a summer that lasts for decades as your world draws closer to the system's brightest star, followed by a winter that stretches for centuries as you enter a phase dominated by the dimmer, cooler suns. The climate would be a roller coaster of extreme temperature swings, potentially giving rise to weather patterns and geological activity far more violent than anything experienced on Earth. These would be worlds of breathtaking beauty and profound danger, where the very laws of nature are written by the intricate dance of 6 separate suns. And within this gravitational whirlwind, some of the most dramatic and bizarre interactions occur not between the stars themselves, but through the stuff that flows between them. In the cosmic close quarters of a sextuple system, the phenomenon of stellar vampirism, where one star siphons material from a companion, evolves from a simple duet into a chaotic, multi-part feeding frenzy. This isn't a gentle transfer, it's a gravitational tug-of-war with 6 participants, creating scenarios so strange they rewrite the textbook on how stars live, age, and die. The stage for this drama is set by a concept called the Roche lobe. Imagine the gravitational influence of a star as a bubble in space. This bubble is its personal territory where its gravity dominates. The point where the bubbles of 2 closely orbiting stars touch is where the material on the surface can most easily flow from one star to the other. In a simple binary system, this can lead to a stable stream of gas, often from a larger, puffier star to a denser, more compact companion like a white dwarf or neutron star. But introduce 4 more stars into this delicate balance, and the entire concept of a stable flow is thrown into disarray. The gravitational tides from the other stars in the system constantly warp and squeeze these Roche lobes. They act like invisible hands, rhythmically pressing on the bubbles that define each star's domain. This can force mass transfer to start prematurely before a star has naturally evolved to fill its lobe, or it can abruptly cut off a stream that would have otherwise been stable for millions of years. A star might be simultaneously pulled by the gravity of 2 or even 3 different companions, its outer atmosphere stretched in different directions like cosmic taffy. This can lead to the formation of complex, looping streams of gas that don't simply flow from one star to another, but instead get flung into intricate webs within the system, sometimes even forming a temporary, shared atmosphere around multiple stars. This creates a scenario of competitive vampirism that is almost unimaginable. Picture a hot, massive star beginning to swell in its old age, its outer layers becoming gravitationally unbound. Instead of having a single predator waiting to feast, it might find itself surrounded. A white dwarf in a tighter orbit could begin siphoning its hydrogen, building up a layer on its surface that might eventually ignite in a runaway thermonuclear explosion, a nova. Meanwhile, a neutron star in a wider orbit could be pulling a separate stream of material onto its magnetic poles, generating intense, pulsing X-ray beams. The donor star is essentially being consumed on multiple fronts, its lifeblood stolen by different vampires for different purposes, drastically shortening its lifespan and leading to an evolutionary path that is utterly unique. The aftermath of this chaotic feeding is written in the altered states of the stars themselves. A star that has been stripped of its hydrogen envelope might be transformed from a red giant into a hot, helium-burning subdwarf, its outer layers now fueling the violent outbursts of its neighbors. The material that isn't cleanly accreted can be ejected from the system entirely or form a complex, dusty circumstellar disk that encircles not one but several stars. This reshuffling of mass can also fundamentally alter the system's gravity, tightening some orbits and widening others, potentially booting a star out of the system entirely or triggering a series of new, unstable interactions. In these dense stellar families, vampirism isn't just a way to extend one star's life, it's a primary engine of change, a relentless force that sculpts the system's destiny through a relentless and chaotic redistribution of its very substance. Astronomers expect a stellar family to share the same birthday. When a massive cloud of gas and dust collapses, it fragments to form stars, but they should all be born within a few million years of each other, a mere blink in cosmic time. This shared origin story is a cornerstone of how we understand star formation. Yet, when we peer into the heart of some sextuple systems, we find a baffling contradiction. stars that are clearly siblings bound by gravity but appear to be separated in age by billions of years. It's like finding a toddler playing in the same sandbox as a pensioner and insisting they are twins. This is the age paradox, a profound mystery that challenges our most fundamental assumptions about how stars are born and how they live their lives. The evidence for this paradox comes from reading the stars themselves, using the light they emit like a cosmic biography. A star's color and brightness tell us its mass and temperature, which we can then cross-reference with stellar evolution models to estimate its age. A massive, hot, blue O-type star burns through its fuel in a furious blaze, living for only a few million years before exploding. A smaller, cooler, red M-type dwarf, by contrast, smolders for trillions of years, barely aging at all. In a typical cluster, all stars follow a predictable pattern on a graph of color versus brightness, known as the Hertzsprung-Russell diagram, tracing a clear line that denotes a single, common age. But in some perplexing sextuple systems, that neat line is shattered. We might find a massive, luminous star that, according to all its characteristics, should have exhausted its fuel and died in a supernova eons ago, yet it shines brightly alongside a collection of faint red dwarfs that are truly ancient. The age gap implied can be staggering. The massive star might appear to be a mere 100 million years old, while its gravitational siblings seem to be 12 billion years old, nearly as old as the universe itself. The models scream that this family cannot possibly exist together, and yet the gravitational data proves unequivocally that they do. This forces astronomers into a difficult choice. Either our methods for dating stars are profoundly flawed, or some bizarre, previously unknown process is actively tampering with the stellar life cycle within these chaotic systems. One compelling explanation points not to magic, but to stellar vampirism on a grand scale, a process that can effectively reset a star's clock. Imagine a close binary pair within the sextuple system where one star begins to evolve faster, swelling into a red giant. Its outer layers become gravitationally vulnerable, and its denser companion star, often a white dwarf, begins to siphon off this hydrogen-rich material. This stolen fuel doesn't just fall onto the surface, it can trigger a transformative event. For the white dwarf, this influx can cause a nova outburst or even cause it to collapse into a neutron star in a supernova. But for the donor star, the effect is even more dramatic. The act of having its outer layers stripped away can reveal its hotter, younger-looking core. What was once an old, inflated red giant is whittled down to a hot, compact, and brilliantly blue helium-burning star. To our telescopes, this stripped-down star no longer looks old and dying. It appears youthful, massive, and full of vigor. Its apparent age is a lie, a cosmic makeover funded by stellar theft. It hasn't been born again. Its old age has simply been peeled away, presenting a deceptive facade of youth that completely skews our interpretation of the entire system's history. This process, called stellar rejuvenation, could be the key to unraveling the age paradox, turning these systems into laboratories for studying the most extreme forms of stellar evolution. Now, to truly understand the nature of these distant suns, we must learn to read their light. Every star has a unique fingerprint, a barcode of dark lines superimposed on its spectrum of colors that reveals its deepest secrets, its temperature, composition, and even its motion. In a solitary star, this spectrum is a clear, singular signature, straightforward to interpret. But in a sextuple system, the light we capture is a tangled chorus, the combined output of 6 different stellar voices all singing their own tune at once. The result is a spectroscopic cacophony, a mess of overlapping lines that would appear to be pure noise to an untrained eye, but to an astronomer, it is a Rosetta Stone for deciphering the system's most intimate details. Untangling this cosmic chorus is a monumental feat of digital detective work. The first challenge is simply identifying which lines belong to which star. A hot, massive O-type star will have strong absorption lines for ionized helium and silicon in its spectrum, signs of its scorching multimillion-degree atmosphere. A cool, diminutive red dwarf, by contrast, will be dominated by the deep, broad lines of molecules like titanium oxide and water vapor. When these spectra are combined in our telescopes, they create a hybrid fingerprint unlike any single star in the universe. Astronomers use sophisticated computer models to perform a technique called spectral synthesis, essentially creating a digital library of every possible stellar spectrum, and then mixing them together in different combinations until they find the precise blend that perfectly matches the observed data. It is a painstaking process of elimination that ultimately reveals the individual identity of each stellar participant. This rare spectral combination offers an unparalleled opportunity for comparative stellar astronomy. Because all 6 stars formed from the same initial cloud of gas, they should, in theory, share an identical chemical composition. The same primordial recipe of hydrogen, helium, and trace metals. By measuring the precise strength of specific element lines in each star's disentangled spectrum, astronomers can test this fundamental assumption with incredible precision. Any deviations become profound clues. If one star shows a higher abundance of lithium, it might suggest that material has been dredged up from its deep interior through convection. If another shows a surprising amount of iron, it could be evidence of a past planetary system that was consumed, its metallic guts enriching the star's outer layers. We are not just looking at 6 stars, we are conducting a controlled experiment on cosmic chemistry, with the system itself providing the control group. The motion captured within these spectral lines adds yet another layer of discovery. As each star in its binary pair orbits its companion, it periodically moves toward us and then away from us. This motion imprints itself on the star's light through the Doppler effect, causing its entire spectral fingerprint to shift slightly toward the blue end of the spectrum as it approaches and toward the red as it recedes. In a sextuple system, we are tracking this subtle dance for 6 stars simultaneously across 3 different orbital periods. By meticulously measuring the timing and magnitude of these shifts over years, we can calculate the mass of each star with extraordinary accuracy. The spectrum thus becomes a precise cosmic scale, allowing us to weigh these distant suns and confirm the gravitational hierarchy of the entire system purely by analyzing the wobbles in their combined light. But the gravitational drama in these systems isn't just a silent movie. It creates ripples that travel across the fabric of the universe itself. When massive objects accelerate through space, they radiate energy in the form of gravitational waves, infinitesimal distortions in spacetime that propagate at the speed of light. For most binary systems, this emission is a slow, steady process, a faint whisper that only the most sensitive instruments can hope to detect after years of observation. In the chaotic heart of a sextuple system, however, this process is supercharged, turning these stellar families into potential factories for some of the most pronounced and complex gravitational wave signals in the cosmos. The key to this intense production lies in the extreme acceleration of the stars involved, particularly within the innermost binary pairs. In a stable, widely separated binary, orbits are leisurely and gravitational wave emission is minimal. But in a sextuple system, gravitational perturbations from the outer stars can constantly inject energy, tightening these inner orbits over time. As the stars are forced closer together, their orbital speed increases dramatically, and this fierce acceleration causes them to radiate gravitational waves far more powerfully. It's the difference between gently twirling a ball on a string and whipping it around in a frantic circle. The energy and the resulting waves are on a completely different scale. This isn't just a single, clean signal. The overlapping orbits create a gravitational cacophony. Imagine trying to listen to an orchestra where 6 instruments are all playing different, rapidly changing tunes simultaneously. The inner tight binary might be emitting a high-frequency, continuous hum as its stars whip around each other in a matter of hours. Meanwhile, the interaction between that binary and the next pair out could be generating a lower frequency modulating beat. And on the longest timescales, the slow, grand orbit of the outermost binary adds a deep, almost imperceptible bass note to the mix. Untangling this complex signal is the ultimate challenge for observatories like LISA, the future space-based gravitational wave detector, but the reward is a direct readout of the system's entire mass and orbital architecture. Detecting these ripples would provide an unprecedented testbed for the laws of physics under conditions of extreme gravity. It could allow us to probe the internal structure of stars themselves, as their tidal interactions during close passages imprint subtle fingerprints on the gravitational wave signal. It might even reveal the presence of exotic objects within these systems, like black holes or neutron stars that have so far remained hidden from our telescopes, their presence betrayed only by the powerful ripples they generate as they dance with their stellar partners. Each wave from a sextuple system is a messenger carrying secrets about the most violent and energetic processes shaping our universe. This glaring gap in the stellar census is more than just a curious statistical anomaly. It points directly to a fundamental difference in how nature builds its largest stellar families. For binary, triple, and even quadruple systems, the prevailing theory is a process known as turbulent fragmentation. A single, massive cloud of gas collapses and breaks apart due to its own internal turbulence and rotation, like a spinning droplet of water splitting into smaller droplets. This process naturally produces a spectrum of systems from singles to quadruples, with the numbers steadily declining as the multiplicity increases. But the near-total absence of quintuples suggests that building a system with 5 or 6 stars requires a different set of blueprints and construction tools entirely. One compelling hypothesis is that sextuple systems aren't built in one go from a single cloud, but are instead assembled through dynamic encounters in the cosmic equivalent of a crowded nursery. Picture the environment where most massive stars are born, a dense, bustling stellar cluster, a place teeming with young suns moving at high speeds. In this gravitational free-for-all, close encounters between systems are common. A pre-existing triple system might have a dramatic gravitational interaction with a binary pair passing nearby. Instead of all the stars scattering, the mathematics of orbital dynamics allows for a possibility where the binary is captured, pulled into a wide orbit around the triple, creating a new, stable quintuple system. But this new arrangement is inherently fragile. This is where the missing quintuples might be hiding. The newly formed 5-star system is likely not in a perfect, stable hierarchical configuration. The gravitational kick from the capture event can leave the orbits misaligned and chaotic, initiating a period of intense dynamical evolution. The system now has a surplus of gravitational energy that it needs to shed to find a stable equilibrium. The most efficient way to do this is to eject the least massive member of the family. This single star is flung out into the cluster, leaving behind a more stable, tighter quadruple system. In this scenario, quintuple systems are not the destination but a fleeting transitional state, a temporary and violently unstable way station on the path to either a quadruple or a sextuple system. So how do we get to 6, the same capture process, but with a specific and more massive starting point? If a pre-existing quadruple system, already a stable, hierarchical configuration, encounters and captures a binary pair, the resulting sextuple system has a much higher chance of stability from the outset. The larger total mass of the quadruple system means the captured binary is more firmly bound from the beginning, and the clear hierarchy of the original 4 stars provides a template that the new pair can slot into without causing catastrophic disruption. The capture of a single star to make a quintuple is messy and unstable, but the capture of an entire pre-formed binary by another pre-formed multiple system can sometimes result in a stable, layered architecture that persists for billions of years. This suggests that the majestic sextuple systems we admire may not be primordial families but rather stellar adoptees, cosmic mergers that forged new and more complex dynasties from the chaos of their stellar birth clusters. These intricate stellar families are not just laboratories for gravity and motion. They are also cosmic forges where the very elements that make up our world are cooked up in wildly unconventional ways. The chemical patterns we observe within some sextuple systems present a bizarre puzzle, showcasing elemental abundances that defy the standard rules of stellar nucleosynthesis, the process by which stars create new elements. In a typical star, the chemistry is a direct reflection of the cloud it was born from, with a dash of elements fused in its own core if it's old enough. But here, the close-quarters interactions between 6 stars create a feedback loop of creation and contamination that results in a chemical signature unlike any other. This unusual enrichment often begins with the life and death of the most massive star in the system. When a giant star reaches the end of its life, it doesn't fade quietly. It explodes in a cataclysmic supernova, forging heavy elements like iron, gold, and uranium in the incredible heat and pressure of the blast and scattering them outward at tremendous speeds. In a solitary star system, this newly forged material would be ejected into the wider galaxy, slowly mixing with the interstellar medium over millions of years. But in a sextuple system, the other 5 stars are sitting right next door, still locked in their gravitational embrace. This proximity means they can be showered with a direct and intense rain of these freshly synthesized elements, a literal stellar fallout that seeds their atmospheres with exotic atoms. We can detect this pollution spectroscopically. A star that should be dominated by hydrogen and helium might show surprisingly strong spectral lines for elements like barium or europium, a telltale sign that it was contaminated by a nearby supernova event. The other primary engine of chemical strangeness is the complex mass transfer we touched on earlier. When one star strips material from another, it isn't just moving hydrogen and helium. That transferred material is often enriched with other elements that were fused deep within the donor star's core and then dredged up to the surface by convection. This can lead to profoundly altered surface compositions. Imagine a star that has been accreting material from a companion that had previously fused carbon in its core. The recipient star's atmosphere might become abnormally rich in carbon, making it appear much older or younger than it truly is based on standard models. In a system with 6 stars, this process can become a multi-stage recycling program. Material might be transferred from star A to star B, then later from star B to star C, each time picking up a new chemical signature before being deposited onto a new host, creating a layered and incredibly confusing history that is nearly impossible to untangle. These bizarre chemical pathways force us to reconsider the grand narrative of galactic chemical evolution, the idea that galaxies become progressively richer in heavy elements over time as generations of stars live and die. That model works on a vast galactic scale, but sextuple systems operate by their own local rules. They can become isolated pockets of extreme chemical enrichment, places where the metallicity, the fraction of elements heavier than helium, is far higher than the surrounding region of the galaxy. Alternatively, the stripping process can create stars that are paradoxically metal-poor, as their outer, enriched layers are removed to reveal the pristine material underneath. This means a single system can contain both a star that is super-metal, rich, and another that appears primordial, a direct contradiction that challenges the very definition of a stellar generation and rewrites the chemical history book on a stellar scale. But how can we possibly map such a complex gravitational web when most of its participants remain hidden in the glare of their brighter siblings? The answer lies not in what we see, but in the impeccable metronomic timing of what we can measure. In an eclipsing binary, when one star passes in front of the other, it causes a predictable, sharp dip in the system's light. In a perfectly stable system, these eclipses would occur with the clockwork regularity of a Swiss timepiece, each one separated by an identical period. Introduce a third, fourth, fifth, or sixth star, however, and this perfect rhythm is thrown into disarray, creating tiny, telltale hiccups in the schedule that reveal the presence and influence of every single body in the system, even those completely invisible to our telescopes. These minute deviations are known as eclipse timing variations, or ETVs. They work on a simple but profound principle. Imagine the central eclipsing binary as a precise clock at the heart of the system. As this pair orbits, the gravitational pull from a distant third star tugs on the entire binary, causing it to wobble slightly around the system's common center of mass. This means that the distance the light from the eclipse has to travel to reach us is constantly changing. When the binary is wobbling toward us, the eclipse appears to happen a fraction of a second early. When it wobbles away, the eclipse is minutely delayed. By meticulously tracking these timing shifts over months and years, astronomers can construct a detailed map of the invisible perturbing body's mass and orbit without ever directly seeing it. It is the cosmic equivalent of finding a hidden object by carefully watching the sway of a pendulum. In a sextuple system like TIC 168789840, this technique becomes a powerful tool for cosmic cartography. We are not just tracking the influence of one hidden star, but multiple. The light curve is a chaotic symphony of eclipses from three different binary pairs. The precise timing of each and every one of these dips is minutely affected by the gravitational pull of the other two pairs. By measuring the timing variations for each set of eclipses independently and then cross-referencing them, astronomers can perform a feat of gravitational triangulation. They can solve for the masses and orbital parameters of all 6 components simultaneously, building a complete and precise model of the entire system's architecture purely from the tiny, accumulated delays and advancements in the eclipse schedule. The data this produces is breathtakingly precise. From these timing variations, we can deduce the mass of an unseen red dwarf to within a fraction of Jupiter's mass. We can determine the shape of its orbit, whether it's circular or highly elliptical, and its inclination relative to the inner pairs. We can even detect the subtle gravitational nudges that the outermost pairs exert on each other, interactions so faint they would be utterly undetectable by any other means. This transforms the system from a mere collection of stars into a precisely calibrated natural scale, where every component has been weighed and measured through its gravitational signature. It allows us to confirm the hierarchical structure, to test the long-term stability of the orbits, and to predict with incredible accuracy what the system will look like thousands of years from now, all by reading the imperfections in its cosmic clock. This relentless gravitational dance begs a monumental question: why stop at 6? After observing the chaos and complexity, one might assume that nature could just keep adding stars, building ever grander families of 7, 8, or even more. Yet, we simply do not find these larger systems. The stark reality is that sextuple configurations appear to represent a fundamental ceiling, a natural upper limit to how many stars can be bound together in a stable, hierarchical structure. This isn't a random occurrence, it is a direct consequence of the unforgiving mathematics of orbital dynamics and the delicate balance required to keep a stellar family from tearing itself apart. To understand this cosmic boundary, we must turn from the telescope to the supercomputer. Astronomers use sophisticated n-body simulations to model these systems, inputting the masses, positions, and velocities of stars, and then letting the laws of physics play out over billions of virtual years. The results are strikingly consistent. While a hierarchical sextuple system with 3 binary pairs can often find a metastable configuration that persists for astronomically long periods, the act of introducing a 7th star, whether as a single star or as a 4th binary pair, almost invariably pushes the entire system past a critical tipping point. The additional gravitational perturbation from that one extra body is frequently the proverbial straw that breaks the camel's back, destabilizing the intricate orbital balances that were barely holding the sextuple system together. The instability manifests in one of two dramatic ways. In the first scenario, the new arrival triggers a gravitational slingshot event. A close encounter between the seventh star and one of the existing members results in a massive transfer of orbital energy. The least massive star in the interaction is often ejected from the system entirely, flung out into the void of interstellar space at tremendous speed to become a rogue nomadic star. The system, having shed the troublesome extra mass, then relaxes back into a stable, simpler state, likely a quintuple or sextuple arrangement. The second, more violent outcome is a direct collision. The perturbed orbits become so radically altered that two stars are sent on a direct intercept course. Their merger is not a gentle blending but a cataclysmic event that releases an enormous amount of energy, potentially triggering a nova and leaving behind a single, more massive star. In both cases, the universe enforces its strict 7-star limit by either ejecting or destroying the excess member. This stability boundary suggests that the sextuple systems we are fortunate enough to observe are not just random occurrences, they are cosmic miracles. They represent the most complex and fragile equilibrium that gravity can possibly sustain. They have somehow managed to form and then survive the turbulent early stages of their life within a dense stellar nursery, avoiding both ejection and collision to settle into their current precarious dance. Each one is a masterclass in gravitational engineering, a natural wonder that has found a way to exist right at the very edge of what the laws of physics will allow, demonstrating that even in the vastness of space, there are strict architectural codes that even the stars must obey. While we often picture star systems in the calm light of the visible spectrum, some sextuple systems reveal their most violent personalities in the high-energy realm of X-rays. The discovery of intense, flickering X-ray sources emanating from these stellar families was completely unexpected, as individual stars like our Sun are relatively quiet X-ray emitters. This powerful radiation points to environments of extreme violence, where gravitational chaos supercharges processes that are merely whispers in simpler systems, turning these stellar collectives into some of the most energetic particle accelerators in the galaxy. The primary engine behind this high-energy spectacle is the brutal gravitational environment itself. In a close binary pair within the sextuple system, stars can orbit each other so closely that their magnetic fields become entangled and enormously amplified. As these stars whip around each other in a matter of hours, their powerful magnetic fields are stretched, twisted, and snapped like cosmic rubber bands. This process, known as magnetic reconnection, acts like a colossal short circuit, explosively releasing immense amounts of energy that heats the local plasma to tens of millions of degrees. At these temperatures, the gas doesn't glow with visible light. It radiates in the fierce, penetrating power of X-rays, creating a brilliant and variable beacon that pulses in rhythm with the frantic orbital dance. Beyond magnetic fury, the other dominant source is the extreme version of stellar vampirism we explored earlier. When material is pulled from one star onto a compact companion like a white dwarf or neutron star, it doesn't just fall quietly. It forms a whirling, superheated disk of accretion around the recipient star. The particles in this disk rub against each other with tremendous friction, heating up to incredible temperatures and emitting X-rays. In a sextuple system, this process is thrown into overdrive. The gravitational tides from the other 4 stars constantly squeeze and perturb this accretion disk, destabilizing it and causing massive clumps of material to suddenly plunge onto the surface of the dense star in violent bursts. This results not in a steady X-ray glow, but in unpredictable, flaring eruptions that can suddenly make the system hundreds of times brighter in X-rays for a short period before fading away. This variability is a key signature, a flickering fingerprint that tells astronomers about the dynamics at play. By monitoring how the X-ray flux changes over time, scientists can untangle the different contributing sources. They might identify a steady, periodic component linked to the orbit of an inner binary, superimposed with random, intense flares from unstable accretion events triggered by the gravitational influence of a passing star from another pair. This makes these systems natural laboratories for studying high-energy physics, allowing us to witness processes of particle acceleration and plasma dynamics under conditions that could never be replicated on Earth, all driven by the relentless and chaotic gravitational dance of 6 stars locked in their intimate embrace. The very existence of these intricate stellar families presents one of the most enduring and heated debates in modern astrophysics. How on Earth, or rather, how in the heavens, do they even form? We are not talking about a simple gathering of stars. We are discussing the architectural planning of a cosmic metropolis where 6 massive gravitational anchors must be carefully placed into a stable, hierarchical structure against nearly impossible odds. The leading theories attempting to solve this formation mystery are as fascinating as the systems themselves, and they each paint a dramatically different picture of the turbulent nurseries where stars are born. The first and most intuitive theory is known as turbulent fragmentation. Imagine a single, colossal cloud of molecular gas and dust, hundreds of light years across and containing enough material to form thousands of stars. As this cloud collapses under its own gravity, it doesn't do so smoothly. Internal turbulence, rotation, and magnetic fields churn the cloud into a chaotic froth, causing it to break apart into smaller, denser clumps. In this model, a sextuple system forms all at once in a single, cascading series of splits. The parent cloud first fragments into 2 or 3 large pieces. But before these larger fragments can fully collapse into individual stars, their own internal turbulence causes them to fragment a second time, each breaking into a tight binary pair. This nested fragmentation event, all happening within a few 100,000 years, could in theory produce the 3 binary pairs that then settle into the hierarchical orbits we observe. The appeal of this model is that it produces a family of stars that are all the same age and share an identical chemical composition, as they all formed from the same pristine cloud. However, the turbulent fragmentation model runs into a significant problem: the sheer scale required. For this cascading breakup to work, the initial cloud must be enormous and possess a very specific and arguably rare combination of turbulence, density, and rotation. Furthermore, the process must happen quickly and efficiently before the first stars formed in the cloud ignite, and their fierce radiation blows the rest of the material apart. It's a delicate cosmic dance that requires everything to go perfectly, which might explain why these systems are so exceptionally rare. The competing and perhaps more compelling theory is dynamic capture. This scenario suggests that sextuple systems are not born as one big happy family, but are instead assembled over time through a series of gravitational encounters in a dense stellar nursery. Picture a young star cluster, a bustling and crowded neighborhood of newborn stars all moving rapidly on chaotic paths. In this gravitational free-for-all, close encounters are common. A pre-existing triple system might have a dramatic brush with a binary pair, instead of a simple gravitational slingshot that sends them flying apart. The complex exchange of orbital energy can sometimes result in the binary being captured, pulled into a wide orbit around the triple. Later, another encounter with a lone star or another binary could add the final member, building the system piece by piece through a form of cosmic adoption. The capture theory elegantly solves the stability problem that turbulent fragmentation faces. A system built through capture is more likely to end up in the stable, hierarchical configuration we observe because the capture process itself tends to eject any stars on unstable orbits. The gravitational interactions during the encounter naturally act as a filter, kicking out the troublemakers and leaving behind only the stars that can settle into a long-term stable arrangement. The main challenge for this model is the chemistry. Stars captured from different parts of the cluster would have formed from different clouds, potentially giving them slightly different chemical fingerprints. Finding such a signature in a sextuple system would be the smoking gun for dynamic capture, forcing us to see these stellar families not as primordial twins, but as gravitational survivors who found each other in the chaos of their youth. For centuries, astronomers have mapped the heavens by tracking the slow, steady drift of stars across the sky, a measurement known as proper motion. It's the real velocity of a star, perpendicular to our line of sight, and for most stars, this motion is a straight, predictable line. But every now and then, we find an outlier, a star whose path isn't straight at all. It wobbles, it zigzags, it dances across the celestial sphere with a tiny, inexplicable anomaly in its motion, a deviation so slight that for generations it went unnoticed. Today, with the incredible precision of space telescopes like Gaia, these proper motion anomalies are no longer hidden. They are glaring signposts, and they are pointing directly to the existence of massive, hidden companions, revealing that what we thought was a solitary star is often the brightest member of a complex, unseen family. This discovery method relies on a simple but profound principle of orbital mechanics. Even if we cannot see a faint companion star, its gravity still tugs on the star we can see. As the visible star and its invisible partner orbit their common center of mass, the bright star is pulled into a tiny circular or elliptical path around that point. From our distant vantage point, this minuscule wobble imprints itself onto the star's otherwise smooth path through space. Over years of meticulous observation, the star's track across the sky will not be a perfect straight line but a gently corkscrewing path. A telltale signature that it is not sailing through the galaxy alone, but is locked in a gravitational embrace with something we cannot yet see. Unraveling this mystery is a painstaking forensic process. The Gaia Space Observatory has been the game changer, providing astrometric data with precision measured in micro-arcseconds, the equivalent of being able to see a coin on the surface of the Moon from Earth. When astronomers analyze Gaia's data for a star with a proper motion anomaly, they can begin to model the hidden perturbing body. The size and period of the wobble reveal the orbital period of the unseen companion and the minimum mass of that object. A small, tight wobble suggests a low-mass companion in a close orbit. A larger, slower wobble points to a more massive partner in a wider orbit. In several remarkable cases, the story did not end with one hidden companion. The anomaly was too complex to be explained by a single gravitational tug. The wobble itself had a wobble. This revealed that the first suspected companion was itself part of a binary pair, and that the entire compact system was being gravitationally influenced by an even more distant fourth object. Through this layered detective work, a star once catalogued as solitary was unmasked as the tip of a vast iceberg, the most visible member of a hidden sextuple system. Its 5 faint companions betraying their presence only by the subtle, gravitational ballet they force upon their brighter sibling. This revelation completely upends our stellar senses. If a system as complex as a sextuple can masquerade as a single point of light for centuries, then how many more are hiding in plain sight? The implications are staggering, suggesting that stellar multiplicity, especially in these extraordinarily complex forms, could be far more common than our traditional surveys have ever indicated. Every star with an unexplained proper motion anomaly becomes a prime candidate for follow-up, a potential gateway into a hidden gravitational labyrinth that challenges our understanding of how star systems form and survive in the crowded galactic disk. And all this chaotic motion generates a force of nature we are intimately familiar with here on Earth, but on a scale that is almost unimaginable: tidal force. Our ocean tides are a gentle, rhythmic pull from our moon and sun, a subtle stretching of our planet's water. But within the close confines of a sextuple system, tidal forces are elevated from a gentle nudge to a dominant, crushing, and world-shattering power. They cease to be a surface effect and become a fundamental driver of stellar evolution, capable of warping the very shapes of suns and churning their internal furnaces in ways that defy all expectations. The principle is the same, but the magnitude is astronomical. Tidal force is the difference in gravitational pull across an object. The side of a star facing a close companion feels a much stronger tug than the side facing away. In a simple binary, this can cause a star to bulge slightly, stretching it into a delicate egg shape. But in a sextuple system, a single star isn't just feeling the pull of one neighbor. It is simultaneously being stretched and squeezed by the combined, ever-changing gravity of 5 other massive bodies. The star isn't just bulging towards one point, it is being pulled in multiple directions at once, its spherical form distorted into a chaotic, pulsating shape that constantly changes as the other stars move through their complex orbits. It is a relentless gravitational assault that never ceases. This extreme distortion has a profound effect on the star's very life cycle. A star's stability and its rate of burning fuel are heavily dependent on its spherical symmetry. The immense gravity and pressure at its core are balanced by the outward push of radiation, creating a stable equilibrium. But when a star is tidally distorted, this perfect balance is disrupted. The regions that are stretched become slightly cooler and less dense, while the compressed regions grow hotter and denser. This disruption can dramatically alter the star's energy output, causing unpredictable flares and changes in brightness that have nothing to do with its internal nuclear processes and everything to do with the brutal gravitational environment it is trapped within. Perhaps the most significant consequence is the triggering of enhanced internal mixing. In a normal, solitary star, the core, where fusion occurs, is often separated from the outer layers. The hydrogen fuel in the core gets depleted, eventually causing the star to evolve into a red giant. But in a star being violently tidally mixed, the constant gravitational kneading acts like a giant spoon, stirring the star's interior. This churning action continually drags fresh, hydrogen-rich material from the outer layers down into the core, while pushing the helium ash produced by fusion outward. This process effectively gives the star a new lease on life, constantly replenishing its core fuel supply and allowing it to burn brighter and longer than a star of its mass ever should. It's a form of forced stellar rejuvenation, making these tidally locked stars appear paradoxically youthful compared to their undisturbed siblings. The ultimate expression of this tidal violence is the potential for a phenomenon known as a tidal disruption event, but on a stellar scale. If the orbits are perturbed just right, a star could be drawn into a dangerously close encounter with a more massive companion. The tidal forces in this scenario would not just distort the star, they would exceed its own gravitational self-binding energy. The star would be literally ripped apart, not in a supernova explosion, but by the sheer tidal pull of its neighbor. Its material would be shredded into a spectacular stream of gas, forming a temporary, superheated accretion disk around the predator star before being consumed. In the chaotic arena of a sextuple system, such catastrophic events are not just possible. They are an inevitable part of the long-term dynamical evolution, a stark reminder of the destructive power lurking within these intricate gravitational dances. Yet beneath the gravitational drama and the spectacular light shows, these stellar families hold a more subtle secret, one written in their very chemistry. When astronomers analyze the light from these 6 stars, they expect to find a consistent chemical fingerprint. After all, they all formed from the same primal cloud of gas and dust, so they should share an identical recipe of elements heavier than hydrogen and helium, a quality known as metallicity. But the reality is a baffling chemical free-for-all. The stars within a single sextuple system can show wildly different metallicities, a paradox that points to a history of cosmic cannibalism and contamination that is anything but straightforward. This metallicity puzzle begins with the standard story of nucleosynthesis. A star fuses hydrogen into helium in its core, and later, if it's massive enough, it forges heavier elements like carbon, oxygen, and iron. When that star dies in a supernova, it scatters these newly minted metals back into space, enriching the surrounding gas from which the next generation of stars will form. This process should ensure that stellar siblings have nearly identical chemical compositions. Finding a significant difference between them is like finding twins with completely different DNA. It shouldn't be possible if they shared the same womb. One compelling explanation for this anomaly is a phenomenon called supernova pollution. Imagine the most massive star in a young sextuple system reaching the end of its short, furious life. It explodes, ejecting a fury of newly forged metals outward at incredible speeds. In a typical loose star cluster, this enriched material would dissipate into the vastness of the galaxy. But in the tight gravitational confines of a sextuple system, the other 5 stars are sitting right next door. They are bathed in a direct, intense shower of this supernova fallout. Their outer atmospheres become contaminated with these exotic elements, making them appear artificially metal-rich compared to their original composition. The key evidence for this would be finding enhanced levels of specific elements, like iron peak elements or even rare radioactive isotopes, in some stars but not others, a clear signature of a nearby cataclysm that occurred after the system's birth. The other, more complex mechanism is sequential mass transfer, a kind of stellar recycling program. In a system with multiple close binaries, material can be stripped from one star and dumped onto another. This isn't just a transfer of pristine hydrogen. The donor star may have already fused heavier elements in its core, and convection may have brought some of this enriched material to the surface. When this metal-rich gas is pulled onto the receiving star, it alters that star's apparent surface metallicity, making it look more evolved than it truly is. This process can become a multi-stage game of chemical hot potato. Element-enriched material might be passed from star A to star B, and then later, a gravitational interaction might cause star B to transfer some of that same material, now mixed with its own unique signature, to star C. The result is a convoluted chemical history where the original pristine signature of the birth cloud is completely overwritten by a complex web of stellar interactions, leaving astronomers to untangle a story of creation and theft written in the subtle absorption lines of 6 different stellar spectra. But even within the complex hierarchy of a sextuple system, the greatest gravitational drama isn't just between individual stars. It unfolds on a grander scale, in the silent, persistent tug of war between the binary pairs themselves. This isn't a simple pull. It's a subtle and cumulative conversation of forces that can either lock the entire system into a harmonious rhythm or send it spiraling toward dissolution. These binary-binary interactions generate resonance effects, a phenomenon where the orbital periods of different pairs become synchronized, forging a gravitational link that can dictate the system's fate for billions of years. Think of it like pushing a child on a swing. If you push at random intervals, your efforts are inefficient and the swing's motion remains erratic. But if you push at the exact right moment in the swing's arc, in resonance with its natural rhythm, each small push adds a significant amount of energy, building a higher and higher arc with minimal effort. In a sextuple system, the gravitational pull from one binary pair acts as that periodic push on another pair. When the orbital periods of 2 pairs form a simple integer ratio, like 2 to 1 or 3 to 2, these tiny gravitational nudges happen at the same point in the orbit every time, amplifying their effect. A resonance locks the pairs into a stable, coordinated dance, their orbits reinforcing each other in a way that can protect the entire system from external perturbations and internal chaos. It's nature's own feedback loop, a celestial mechanism that actively enforces order. However, this same mechanism has a terrifyingly destructive double edge. A system can fall into a destabilizing resonance just as easily as a stabilizing one. If the periodic tugs from an outer binary pair consistently occur at the worst possible point in the inner binary's orbit, they can act like a relentless, gravity-powered hammer, repeatedly striking at the orbit's most vulnerable point. Instead of reinforcing stability, these antagonistic resonances pump energy into the system, increasing the eccentricity of the orbits, making them more elongated and elliptical. This drives the stars to pass dangerously close to one another at periastron, their point of closest approach, dramatically raising the risk of tidal stripping, collision, or gravitational slingshots that can eject a star from the system entirely. The difference between a stabilizing and a destabilizing resonance can be a matter of a few percent in the orbital period, a razor-thin margin between cosmic harmony and celestial catastrophe. These resonant interactions create evolutionary paths that are utterly unique to high multiplicity systems. A sextuple system might spend hundreds of millions of years in a stable configuration, its pairs gently locked in a gravitational accord. Then, a slow and subtle change, perhaps the gradual loss of mass from one star through stellar winds, can shift the orbital periods just enough to break that stabilizing resonance and push the system into a new, destructive one. This can trigger a phase of violent dynamical evolution that lasts for a few million years, a frantic period of chaotic interactions that ejects one or two stars and completely reorders the remaining hierarchy, leaving behind a stable quadruple system. The system doesn't just age, it metamorphoses, leaping from one stable state to another through short, violent upheavals dictated by the delicate and ever-changing gravitational conversations between its constituent pairs. This symphony of light and shadow reaches a crescendo in the baffling variability of these systems, where the combined effects of eclipses, pulsations, and rotational modulation produce light curves so complex they initially appeared to be pure noise. For an astronomer, a light curve is a story, a graph of a star's brightness over time that typically tells a clear tale of a planet passing in front of it or a companion star eclipsing its light. But the data streaming in from these stellar families was a chaotic, indecipherable scribble, a cryptographic puzzle that seemed to defy all known classification. It wasn't just messy, it was unlike anything in the existing catalogues of variable stars, presenting a challenge that required a complete rethinking of how to interpret the light from a single point in the sky. The root of this confusion lies in the sheer number of overlapping signals. Imagine trying to listen to three separate songs playing at the same time, each with its own rhythm, melody, and volume changes. Now imagine that one of those songs is a steady drumbeat of eclipses, another is the gentle, sinusoidal wave of a pulsating star rhythmically expanding and contracting, and the third is the slow, steady fade of rotational modulation as a star with a giant sunspot turns on its axis. In a sextuple system, you are not just hearing three songs at once. You are hearing all six stars contributing their own unique audio tracks to this cosmic cacophony, and the resulting mix is a sonic labyrinth that initially sounds like pure static. Before the true nature of these systems was understood, this led to a series of hilarious and humbling misclassifications. Automated survey algorithms trained on clean, single-cause variable stars would often spit out a best guess that was wildly off the mark. A system might be flagged as a potential cataclysmic variable, a binary with explosive outbursts because of a sudden, sharp dip in brightness that was actually just the fortuitous alignment of two separate eclipses happening nearly simultaneously. Another might be classified as a pulsating giant star with an inexplicably messy signal, when in reality the mess was the predictable but overlapping flicker from several different stars. The data was trying to tell a story of six stars, but we only had the vocabulary for one. The key to cracking this code was the application of advanced computational power and a technique known as Fourier analysis. This mathematical tool acts like a cosmic prism, taking that messy, combined light curve and splitting it apart into its individual constituent frequencies. It can isolate the precise, repeating signal of a 2-day eclipsing binary from the slower, 40-day rhythm of a pulsating star and the even more gradual 80-day signature of a rotating star with a massive starspot group. By meticulously extracting and then subtracting each identified signal one by one, astronomers could finally see the underlying patterns emerge from the noise. What was once an incomprehensible jumble was revealed to be a perfectly orchestrated, albeit incredibly complex, gravitational and photometric ballet. This process didn't just solve a puzzle, it provided a new set of tools for diagnosing the hidden structure of other complex systems, turning a source of confusion into a powerful new method of discovery. But what happens when the gravitational tides we've explored become so overpowering that they don't just distort a star, but completely seize control of its rotation? In our own solar system, we see a simple version of this. Our moon is tidally locked to Earth, forever showing us the same face. Now amplify that concept by a factor of 6. Within the tightly wound gravitational web of a sextuple system, tidal locking evolves from a simple partnership into a chaotic, multi-body negotiation over spin states and angular momentum, leading to some of the most bizarre and counterintuitive stellar behaviors imaginable. The fundamental goal of tidal forces is to achieve a state of synchronization, where a star's rotational period perfectly matches its orbital period around its immediate companion. In a calm binary system, this is a straightforward process that eventually leads to a stable, locked configuration. But introduce 4 other massive gravitational players into the equation, and this simple goal becomes an impossible dream. A star might be desperately trying to tidally lock to its closest binary partner, but it is simultaneously being wrenched and pulled by the gravity of the other stars in the system. Their persistent tugs act like external hands constantly grabbing the spinning star, preventing it from ever settling into a steady, synchronized rhythm with any one body. This relentless gravitational interference can force stars into what are known as spin-orbit resonances, states far more complex than simple locking. Instead of rotating once per orbit, a star might be forced into a spin that completes 3 rotations for every 2 orbits, or other non-integer ratios. These resonant states are highly unstable and can drive incredible internal heating within the star. The constant, asynchronous flexing and kneading of its structure by the changing tidal forces generates friction deep in its interior, acting like a gravitational engine that supplements the star's nuclear fusion and can cause it to glow unexpectedly bright in infrared wavelengths, a telltale sign of this tidal torture. The distribution of angular momentum, the intrinsic spininess of the entire system becomes a frantic game of cosmic hot potato. In a solitary star, all its angular momentum is contained in its own rotation. But in these complex families, angular momentum is constantly being transferred. It can be stolen from a star's spin and injected into its orbit around a companion, making the orbit wider. Conversely, orbital energy can be dissipated and converted back into rotational spin. With 6 stars all doing this simultaneously, the entire system is a swirling, dynamic reservoir of angular momentum that sloshes between stellar rotations and orbital paths, never settling into a quiet equilibrium. This endless exchange can actually help stabilize the system against catastrophic collapse, acting as a gravitational shock absorber that lets the stars bleed off excess energy through these subtle spin-orbit adjustments. The most extreme outcome of this multi-body tug-of-war is the potential for a star to become super-synchronized, spinning at a rate that is actually faster than its orbital period. This sounds like it defies physics, but it's a direct result of the combined tidal forcing from multiple directions. The star is essentially being overwhelmed by the conflicting gravitational pulls, its rotation whipped into a frenzy that makes it spin on its axis in a matter of hours instead of days. This hyper-rotation can have dramatic consequences, amplifying the star's magnetic field to extreme levels and turning it into a prodigious generator of stellar flares and violent X-ray emissions, a brilliant and chaotic lighthouse amidst the quiet darkness of space. And just when we thought we had seen every form of cosmic architecture, these stellar families reveal another layer of complexity, one that extends beyond the stars themselves into the very material that might one day form planets. We tend to imagine planet-forming disks as neat, flat, orderly rings, like Saturn's rings on a grand scale, spinning peacefully around a single star. But within the gravitational whirlwind of a sextuple system, these disks are not peaceful at all. They are warped, twisted, and sculpted into bizarre and magnificent structures by the relentless pull of 6 suns, creating dust and debris formations unlike anything we see around solitary stars. The chaos begins from the very moment a disk starts to form. In a calm, single-star system, a protoplanetary disk can rotate serenely for millions of years. But place that same disk within the gravitational sphere of influence of 5 other massive bodies, and it enters a state of perpetual torment. The competing gravitational tides act like immense, invisible hands, constantly squeezing, stretching, and perturbing the disk from multiple directions at once. This doesn't just gently shape the disk, it can violently truncate it, sharply cutting off its outer edge and dramatically limiting the amount of material available for planet formation. In the most extreme cases, these forces can rip the disk apart entirely, scattering its precious planetary building blocks into the void before they can even begin to coalesce. Yet, against all odds, some disks not only survive this gravitational assault, they are forged by it. The same forces of chaos can also trigger waves of intense creation. Gravitational perturbations can slam into the disk like a hammer, triggering powerful density waves, ripples that force dust and gas to pile up in specific regions. These become cosmic construction zones, accelerating the collisional growth of dust grains into planetesimals at a breakneck pace. It's a high-risk, high-reward scenario. While many potential planets are likely shredded or ejected by the unstable environment, those that do manage to form are born in a crucible of extreme physics, emerging as some of the most exotic and resilient worlds we can possibly conceive. The resulting disk morphologies are breathtakingly strange. Instead of a single, continuous ring, we see multiple, misaligned disk components. One binary pair might host a tight, compact dust ring nestled close to the stars, while another pair in the system supports a much larger, more diffuse debris disk at a completely different orbital inclination. The gravitational pull from the other stars can torque these disks, twisting them into dramatic spirals or warping them into pronounced saddle shapes that precess over time. In some systems, the entire disk structure might not even be centered on a single star, but instead form a vast circumsystem ring that encircles the gravitational center of mass of the entire sextuple system, a gargantuan belt of material feeding all 6 of its stellar masters. This environment creates the potential for planetary system architectures that defy all convention. We could not simply have planets in nice, circular orbits around a single sun. Instead, we might find P-type planets worlds that orbit the entire central quadruple system on a wide, precarious path, or S-type planets that cling desperately to a single star within one of the binary pairs, their skies filled with multiple suns whose gravitational influence constantly tugs at their orbit, threatening to fling them into the void. The concept of a habitable zone, that Goldilocks region where liquid water could exist, becomes a dizzying 4-dimensional map, shifting not just with distance, but with the ever-changing positions and luminosities of 6 different stellar heat sources. Now consider the invisible architecture woven between these stars, not just gravity but magnetism. Each of these 6 spinning suns generates its own powerful magnetic field, a vast, invisible bubble of influence that extends far out into space. In a solitary star, this field might create the occasional sunspot or solar flare, but in the chaotic close quarters of a sextuple system, these individual magnetic bubbles don't just coexist. They collide, merge, and violently interact, weaving a tangled web of magnetic force that connects all 6 stars into a single, system-wide circuit of phenomenal power. This creates a magnetospheric environment of such complexity that it dwarfs anything we see in our own solar neighborhood. The stage for this drama is set by the stars themselves, particularly the cool, red dwarfs that are common in these systems. These stars are known for their ferocious magnetic personalities. They are fully convective, meaning their entire interior is constantly churning like a pot of boiling water. This relentless motion acts like a dynamo, amplifying their magnetic fields to strengths thousands of times greater than our Sun's. When 2 such stars in a tight binary pair orbit each other, their powerful magnetic fields become entangled, spinning and snapping like colossal rubber bands. This process, known as magnetic reconnection, acts like a celestial short circuit, explosively releasing immense amounts of stored energy. The result is a super flare, an eruption of radiation so powerful it can briefly outshine the combined light of both stars, bathing every other member of the sextuple system in a torrent of X-rays and ultraviolet light. But the true strangeness emerges from the connections between the different binary pairs. The magnetic fields from one duo can, under the right conditions, extend out and actually link up with the fields from another pair, creating magnetic bridges across vast distances within the system. This isn't a gentle connection, it's a channel for instability. A flare on one star can trigger a sympathetic flare on another star light years away across the system, not through proximity, but through this magnetic linkage. It's as if the stars are connected by invisible wires, allowing activity on one to instantly reverberate across the entire family. Astronomers could observe a cascade of flares, one triggering the next, racing through the system in a wave of synchronized stellar violence. This connected magnetosphere also leaves a visible imprint on the star's surfaces. The powerful, system-wide magnetic forces can suppress convection in specific regions, leading to the formation of gigantic star spots, dark, cooler patches on the stellar surface. Incredibly, these spots can appear correlated. Observations might reveal that a star in the inner binary and a star in the outermost pair both develop massive spot groups at the same time, and that these spots rotate into and out of view in a synchronized rhythm, despite the stars having vastly different rotation rates. This suggests that the system's global magnetic field is somehow orchestrating stellar activity across all 6 members, imposing a kind of magnetic harmony on the gravitational chaos. For an observer on a hypothetical planet, this could mean not just cycles of light and dark from the star's orbits, but cycles of intense radiation and magnetic storms that sweep through the entire system on a schedule dictated by the invisible field lines connecting its 6 dancing suns. Looking billions of years into the future, these intricate stellar families face evolutionary paths so divergent and spectacular that they read like the climax of a galactic epic. Every sextuple system is engaged in a slow-motion race against time, a battle between nuclear fusion in their cores and the relentless pull of gravity that seeks to pull them apart. The eventual fate of each system is not written in stone but is instead a complex probability cloud, shaped by the precise masses, orbits, and the unpredictable whims of gravitational chaos that will play out over eons. Their endgame possibilities range from a symphony of synchronized stellar deaths to a silent, gradual unraveling, each outcome leaving behind a profoundly different cosmic monument. One of the most explosive potential finales involves the system's most massive members. If the system contains stars weighing in at over 8 solar masses, their lives will end not with a whimper, but in a series of cataclysmic supernovae. The timing and sequence of these explosions are critical. If the first supernova occurs symmetrically, the dying star might eject its outer layers evenly, leaving behind a dense neutron star or black hole without giving its binary partner a significant gravitational kick. The system could potentially survive this violent loss, recalibrating its orbits to accommodate the new, incredibly dense remnant. This opens the door to forming a system containing a bizarre menagerie of stellar corpses. A neutron star orbiting a main sequence star, itself locked in a dance with a white dwarf pair, all encircled by a distant binary of red dwarfs. Such a graveyard of stars would be a prime source of gravitational waves and a laboratory for extreme physics. However, the more likely outcome is that a supernova is a deeply disruptive event. The sudden loss of a significant fraction of the system's mass, literally blown away in the explosion, can instantly destabilize the delicate gravitational equilibrium that has held the family together for billions of years. The released energy and the possible asymmetric kick imparted to the newborn neutron star can act like a bomb going off at the heart of the system. Orbits that were once stable become wildly elliptical or even unbound. The result is often a gravitational slingshot, where the least massive members are flung out of the system at incredible speeds to become hypervelocity runaway stars, destined to wander the interstellar void alone. The remaining stars, now with a new black hole or neutron star in their midst, might collapse into a tighter, more chaotic configuration, setting the stage for further violent interactions. Another path leads not to explosion, but to a slow and silent decay through gravitational radiation. For the innermost, tightest binary pairs, the constant emission of these ripples in spacetime acts as a brake, relentlessly sapping their orbital energy. Over trillions of years, a timescale that stretches beyond the current age of the universe, these orbits will slowly decay, drawing the two stars closer and closer together. In a system containing white dwarfs, this could lead to a series of collisions or mergers. Two white dwarfs merging could surpass the Chandrasekhar limit, triggering a Type Ia supernova that would likely sterilize the entire system. Alternatively, if a white dwarf is pulled onto a neutron star, the resulting accretion could create powerful X-ray bursts or even a kilonova, blasting the surrounding space with heavy elements like gold and platinum. The quietest in-game is one of complete gravitational disintegration. For systems that are already loosely bound, particularly those with a wide outer binary, the cumulative effect of countless weak gravitational perturbations, from passing molecular clouds, other stars, and even the overall tidal force of the galaxy itself, can slowly erode the tenuous links that hold them together. Over billions of years, the outermost pair first drifts away, its orbit stretched so wide by external influences that it effectively becomes unbound, leaving behind a quintuple system. This process continues with the next most loosely bound star or pair being stripped away, a gradual peeling of the cosmic onion. The end result is not a grand explosion, but a quiet dissolution. The once majestic sextuple system would slowly separate into a collection of isolated single stars and tighter binaries, all drifting apart on their own trajectories through the galaxy, their shared history erased and their former connection becoming undetectable. Each of these potential finales leaves its own unique fingerprint on the galactic landscape, a testament to the dynamic and ultimately transient nature of even the most complex structures in our universe. Yet within this gravitational whirlwind, a tantalizing question emerges: could life find a way in such an environment? The search for habitability in sextuple systems pushes the concept of a Goldilocks zone to its absolute limit, transforming it from a neat, circular region around a single star into a dynamic, evolving four-dimensional map that shifts with the ever-changing positions and luminosities of 6 different suns. A planet here wouldn't experience a consistent year with predictable seasons. Its climate would be dictated by a chaotic symphony of gravitational perturbations and wildly variable illumination, creating exotic environments unlike anything we've theorized for solitary star systems. The first and greatest challenge for any potential world is simply achieving a stable orbit. The combined gravitational pull from 6 massive bodies creates a minefield of orbital resonance zones, regions where the periodic tugs from different stars would amplify a planet's eccentricity until its path became so elongated it would either be ejected from the system or collide with another body. Stable orbits could only exist in specific, finely tuned pockets, likely very close to one star in a tight binary pair, or on a wide, delicate path that encircles the entire central cluster of stars. A planet surviving here would need to navigate a celestial obstacle course for billions of years, its path constantly adjusted by subtle gravitational influences from its multiple stellar masters. The light and heat such a world receives would defy all earthly conventions. Imagine a day where 3 suns hang in the sky at once, a brilliant blue giant, a milder yellow star, and a dim red dwarf, each contributing a different quality of light and radiation. Periodically, these stars would eclipse one another, creating sudden, dramatic dips in brightness where the temperature could plummet hundreds of degrees in minutes. The very definition of day and night becomes meaningless when your world might experience periods of near-constant daylight from multiple sources followed by a brief, profound darkness when all 6 stars dip below the horizon. Photosynthesis, if it could occur at all, would have to adapt to this wildly variable light spectrum, potentially evolving to harness different wavelengths from different suns at different times. These exotic illumination patterns would create weather and climate systems of unimaginable violence and complexity. The extreme temperature gradients between the illuminated and dark sides of the planet could generate supersonic winds, constantly redistributing heat across the surface. The gravitational pull from multiple stars would exert tremendous tidal forces not just on any oceans, but on the planet's very crust and atmosphere, potentially triggering global volcanic activity that constantly replenishes the atmosphere against stripping by intense stellar winds. A habitable world here wouldn't be a tranquil oasis. It would be a rugged survivor, a planet forged in the most extreme crucible nature can provide, where life would need to endure conditions that make Earth's most hostile environment seem placid by comparison. Among the most energetic phenomena in our galaxy are microquasars, stellar systems that fire powerful jets of particles at nearly the speed of light. These are essentially scaled-down versions of the supermassive black holes that power distant quasars at the heart of galaxies. For decades, we believed these cosmic particle accelerators were primarily the product of binary systems, where a compact object like a black hole or neutron star pulls material from a companion, forming an accretion disk that can launch these spectacular jets. But the discovery of potential microquasar activity within some sextuple systems has completely upended that simple picture, suggesting that the gravitational chaos of a 6-star family might be the ultimate engine for creating these high-energy beasts. The connection makes a disturbing kind of sense when you consider the raw ingredients needed. To form a sustained microquasar, you need a stable and prodigious source of fuel for the accretion disk, and you need a mechanism to power and collimate the jets. A simple binary can provide this, but often only intermittently. Now, imagine the same scenario, but the compact object isn't just feeding from one star. It's sitting at the heart of a gravitational nexus with 5 other potential donors. The sheer abundance of available fuel is staggering. A stream of material could be pulled from a puffy giant in a close orbit, while the gravitational tides from a wider binary pair constantly perturb and funnel additional gas into the system. This creates a feedback loop of plenty, ensuring the accretion disk around the central compact object is never starved, a key prerequisite for launching and sustaining those powerful, continuous jets. Furthermore, the complex magnetic environment of a sextuple system could provide the perfect mechanism to collimate those jets. The powerful, intertwined magnetic fields generated by the multiple stars can act like a cosmic funnel, channeling the outflowing particles from the accretion disk into tight, focused beams. It's the difference between a garden hose spraying water everywhere and that same hose fitted with a precision nozzle. The magnetic fields from the surrounding stars provide that nozzle, creating the intensely focused jets we observe. This means the sextuple system isn't just a fuel depot, it's also the factory and the launch facility, providing all the necessary components to build and fire a microquasar right in our cosmic backyard. This revelation transforms our understanding of how these high-energy systems form and persist. A microquasar in a sextuple system isn't a fleeting event. It could be a semi-permanent feature, a constant engine of destruction and creation running for millions of years. The intense radiation from its jets would bathe every other star in the system, stripping atmospheres, evaporating protoplanetary disks, and fundamentally altering the chemical makeup of the entire family. It turns the sextuple system into the ultimate high-energy astrophysics laboratory, a place where we can study the particle acceleration and jet formation processes of active galaxies, but located thousands of light years away instead of billions. But within this swirling gravitational chaos, one of the most perplexing discoveries is not a deviation from the norm, but an appearance of unexpected order. For all their dynamic fury, some sextuple systems exhibit a strange and precise cosmic choreography. The orbital planes of their different binary pairs are not randomly tilted but show a surprising degree of alignment. This finding is deeply counterintuitive. With so many gravitational interactions constantly pulling and tugging over billions of years, we would expect these orbits to be scrambled into every possible orientation, a tangled mess of inclinations. The fact that some systems retain this alignment is a profound clue, a silent whisper from their violent birth that has somehow persisted against all odds. This phenomenon, often called coplanarity, points directly back to the system's origin. The leading theory suggests it is a fossilized record of the initial angular momentum of the primordial gas cloud from which all 6 stars were born. As that single, massive cloud began its gravitational collapse, it was undoubtedly spinning. This rotation would have flattened the cloud into a vast disk, much like a spinning ball of pizza dough flattens out. If the cloud then underwent hierarchical fragmentation, splitting first into smaller clumps that themselves split into binaries, all of those fragments would have inherited the same dominant direction of spin from that original parent disk. Their individual orbital planes would therefore all lie within the same general plane, preserving that initial angular momentum blueprint for billions of years. In this scenario, the alignment is a birthmark, a vestige of the system's first moments. However, nature is rarely so simple, and an alternative, more dynamic explanation exists. It's possible that these orbits were not born aligned, but were forcibly realigned later through a process called secular dynamical evolution. This is a slow, gravitational process where the distant, persistent tug of war between the binary pairs themselves can actually cause their orbits to gradually torque and precess. Over immense timescales, this interaction can dampen their mutual inclinations, driving the entire system toward a flatter, more coplanar configuration. It's a gravitational negotiation that finds the most stable, lowest energy state for the complex system, effectively ironing out the wrinkles in its orbital architecture long after the stars themselves had formed. Distinguishing between these two origins, a primordial birthmark or a later gravitational settling, is an active area of research. The key evidence lies in the specifics of the alignment. A system that formed with its orbits perfectly coplanar might show other chemical homogeneities or a very specific mass hierarchy. A system that achieved alignment later through dynamical processes might host older, more evolved stars or show subtle signs of past gravitational trauma in the eccentricities of its outer orbits. Each aligned system we find is therefore a cosmic cold case, and by measuring the precise angles between these stellar orbits, we are reading the evolutionary history of the entire family, uncovering whether the order we see today was there from the very beginning or is the hard-won prize of a billion-year gravitational struggle. Now let's venture into the theoretical, where the exotic becomes almost unimaginable. Consider the possibility of a pulsar nestled within one of these stellar families. A pulsar is the ultra-dense, rapidly spinning corpse of a massive star that died in a supernova, a neutron star that beams radiation from its magnetic poles like a cosmic lighthouse. If that beam sweeps across Earth, we detect it as an exquisitely precise radio pulse, a metronomic tick that is among the most reliable clocks in the universe. Now place this perfect natural clock into the gravitational whirlwind of a sextuple system. The result would be the most demanding and spectacular test of Einstein's theory of general relativity ever conceived. The power of a pulsar lies in the incredible precision of its timing. Any deviation in the rhythm of its pulses is not noise, it is a message. A slight delay or advance in the arrival time of a pulse can be caused by the pulsar moving through the gravitational wells of its 5 stellar companions. In a simple binary system with a pulsar, these subtle delays have already allowed us to confirm predictions of general relativity with stunning accuracy, such as the orbital decay due to gravitational wave emission. But in a sextuple system, the complexity is magnified by orders of magnitude. We would not be measuring the influence of one other star, but 5. The pulsar's pulse arrival times would carry the combined gravitational imprint of every single massive body in the system, each tugging on it and the light it emits in a unique way as they move through their intricate orbits. This would allow us to perform a form of gravitational tomography, mapping the entire mass distribution of the system in 3 dimensions solely by how it warps spacetime around the pulsar. We could measure the masses of all 6 stars with unparalleled precision, even for those that are completely dark and invisible to our telescopes. The timing data would reveal not just their masses, but the precise shapes of their orbits and their mutual inclinations. It would be the ultimate validation of the system's hierarchical model, providing a complete and precise gravitational blueprint built from the tiny, accumulated delays in a spinning stellar corpse's beacon. The most thrilling prospect is the potential to probe for deviations from general relativity itself. The theory has passed every test we've thrown at it so far, but it has never been tested in the gravitational field of 6 closely interacting masses. The extreme curvature of spacetime in the heart of such a system could reveal subtle effects that only manifest in these unique environments. Does gravity behave exactly as Einstein predicted when stacked and layered in such a complex way? A pulsar here would be our probe, its flawless tick sensitive to any minute crack in our understanding of the universe's fundamental force. Finding such a system would transform it from a celestial curiosity into the most important gravitational laboratory in the galaxy. The hunt for these cosmic rarities is entering a new golden age, driven not just by bigger telescopes, but by smarter ways of seeing. The challenge is immense. Finding a sextuple system is like listening for a single, unique conversation in a stadium of cheering fans. Traditional methods, while powerful, are reaching their limits. The next wave of discovery will come from a suite of advanced technologies specifically designed to untangle the incredibly complex signals these systems emit, pushing the very boundaries of observational astronomy. We are on the cusp of moving from stumbling upon these giants by chance to actively hunting them down with precision tools. At the forefront of this revolution is machine learning. The chaotic, scribbled light curves that once baffled astronomers are now the perfect training data for sophisticated artificial intelligence algorithms. These systems are not programmed with fixed rules. Instead, they are shown thousands of simulated light curves, some from simple binaries, others from complex sextuples, and they learn to identify the subtle, hidden patterns that distinguish them. An AI can process decades of observational data in hours, flagging stars with that specific brand of photometric madness that indicates multiple overlapping eclipses and pulsations. It can sift through millions of light curves from surveys like TESS or the upcoming Pluto mission, performing the initial, grueling detective work and presenting astronomers with a shortlist of the most promising, bizarre candidates for follow-up, turning a needle in a haystack search into a targeted investigation. Beyond light, we are learning to read the stellar wobble with unprecedented precision through advanced radial velocity techniques. The standard method measures the Doppler shift of a star's spectral lines to detect the tug of an orbiting companion. But in a sextuple system, the signal is a cacophony of multiple overlapping wobbles. The next generation of ultra-stable spectrographs, like the espresso instrument on the Very Large Telescope, are achieving such phenomenal precision that they can begin to disentangle this mess. They can detect velocity changes measured in centimeters per second, a walking pace allowing us to not just detect the presence of multiple companions, but to start building a precise model of their masses and orbits directly from the starlight, even for the faintest and most tightly bound pairs. The future, however, belongs to a new generation of space observatories designed with stellar multiplicity in mind. The European Space Agency's Pluto mission, launching later this decade, is a planet hunter that will also be a sextuple system finding machine. Its strategy is to stare at huge patches of the sky for years at a time, gathering ultra-precise, continuous light curves for hundreds of thousands of stars. This long baseline is crucial, as it will finally capture the incredibly slow, faint eclipses and timing variations caused by the wide, outer binary pairs in these hierarchical systems, components that have largely remained invisible in shorter surveys. Even more revolutionary is the promise of optical interferometry from space. Imagine a fleet of small telescopes flying in precise formation, millions of kilometers apart, acting as one giant virtual telescope with a resolution so sharp it could, in theory, directly image the individual stars in a nearby sextuple system. A mission like this could resolve the pinpricks of light from each component, measuring their separation and motion directly, moving us from inference to direct observation. This would allow us to create a dynamic movie of their gravitational dance, providing the definitive proof of their orbits and putting our complex models to the ultimate test. Perhaps the most profound future detection method lies not in light, but in the ripples of spacetime itself. The Laser Interferometer Space Antenna, or LISA, will be a gravitational wave observatory sensitive to the low-frequency hum produced by massive orbiting objects. The innermost, tightest binaries in a sextuple system, particularly those containing white dwarfs or neutron stars, will be prolific sources for LISA. It will detect their steady gravitational wave signal, but crucially, it will also detect the tiny perturbations in that signal caused by the gravitational pull of the other four stars in the system. By analyzing this complex gravitational wave fingerprint, we will be able to deduce the entire system's architecture, the masses and orbits of all 6 stars, even if some of them are completely dark, like black holes or faint red dwarfs, revealing systems that are otherwise completely invisible to any telescope that relies on light. From the first realization that Castor was not one but 6 stars, to the mind-bending detection of a system where all 3 pairs eclipse from our vantage point, every discovery about these celestial families has forced us to rewrite the cosmic rulebook. We've explored how they defy the very notion of stability, existing on a razor's edge where gravitational chaos can lead to stellar collisions, violent ejections, or a frantic redistribution of mass through multi-star vampirism. We've seen how their sheer multiplicity warps the possibility of planet formation, creating worlds with 6 suns and climates of unimaginable complexity, and how their intertwined magnetic fields can ignite system-wide stellar flares, connecting all members in a web of violent energy. These are not calm, orderly systems. They are dynamic, chaotic, and extreme laboratories where the laws of physics are tested under conditions we once thought impossible. The existence of these systems challenges the core of our stellar formation theories, presenting us with the age paradox, where stellar siblings appear billions of years apart, and forcing us to choose between the neat story of turbulent fragmentation and the dramatic assembly of dynamic capture. They have revealed themselves through tiny wobbles in a star's motion, through minuscule delays in the flawless ticks of a pulsar's clock, and through the chaotic scribble of a light curve that only machine learning can now decipher. Each revelation, from tidal forces that crush stars into new shapes to gravitational wave signatures that hum with the system's entire history, pulls back a deeper layer of mystery, showing us that the universe's capacity for invention far exceeds our imagination. As our technology evolves, with missions like Pluto and Lisa on the horizon, we stand on the brink of discovering countless more of these gravitational marvels. Each new system will be a fresh chapter in this story, potentially revealing even more exotic configurations, perhaps ones with 7 stars, or systems where the stellar residents are all black holes or neutron stars. The search is no longer about mere discovery. It is about deepening our fundamental understanding of how gravity builds order from chaos, how stars live and die in the most social of settings, and how the most unlikely corners of the universe might just harbor the conditions for strange new worlds. We have looked into the heart of these 6 star systems and found not just complexity, but a reflection of the universe's boundless creativity. Now we want to hear from you. Which of these 30 discoveries shattered your expectations the most? Was it the potential for habitable planets with 6 suns, the stellar vampirism feeding frenzy, or the sheer gravitational ingenuity that keeps them from flying apart? Share your thoughts in the comments below. The hunt for these cosmic rarities is shifting from chance encounters to a deliberate, high-tech treasure hunt, driven by a new generation of observatories and space missions specifically designed to untangle the incredibly complex signals these stellar families emit. Ground-based surveys like the Vera-C, Rubin Observatory's legacy survey of space and time, are set to scan the entire southern sky every few nights for a decade, not just capturing snapshots but creating a high-definition movie of the cosmos. Its unprecedented combination of a vast field of view and deep sensitivity will allow it to monitor billions of stars for the telltale, complex variability that betrays the presence of multiple eclipsing pairs orbiting each other, automatically flagging thousands of new candidates for complex systems that would have otherwise remained hidden in the noise of older, less capable surveys. But the true revolution in understanding will come from instruments that can move beyond mere detection and into detailed forensic analysis. The James Webb Space Telescope, with its colossal infrared sensitivity, acts like a cosmic ultrasound, allowing us to peer into the dusty, obscured stellar nurseries where these systems are born. It can dissect the light from young, still-forming sextuple prototypes still embedded in their natal clouds, measuring the chemical composition and dynamics of the gas flowing between the stellar embryos. This gives us a real-time look at the hierarchical fragmentation process in action, watching as a massive cloud breaks apart into smaller clumps that themselves collapse into binaries, providing the first direct evidence for how these architectural marvels are built. The next leap will be in sheer resolution, delivered by the upcoming extremely large telescopes. The ELT, with its 39-meter primary mirror, and its cousins the Giant Magellan Telescope and the 30-meter telescope, will possess an astonishing ability to resolve fine detail. They will be capable of directly imaging and spectroscopically analyzing the individual stars within nearby sextuple systems, separating the light of a brilliant blue giant from its faint red dwarf companion, even when they are separated by a distance equivalent to that between the Sun and Uranus. This moves us from inferring the system's architecture based on complex light curves to directly watching the stars move along their predicted paths over years of observation, creating a dynamic map of their gravitational dance and putting our complex stability models to the ultimate test. These colossal ground-based eyes will be complemented by a new ear listening to the universe, the space-based gravitational wave observatory LISA. while ground-based detectors like LIGO hear the high-frequency chirps of merging black holes, LISA will be tuned to the low-frequency hum of millions of binary systems, including the tight inner pairs within sextuple families. Its most profound contribution will be detecting the subtle perturbations in that steady hum caused by the gravitational pull of the other stars in the system. By analyzing this complex gravitational wave fingerprint, LISA will be able to deduce the entire system's architecture, the masses and orbits of all 6 stars, even for components that are completely dark, like black holes or faint red dwarfs, revealing systems that are utterly invisible to any telescope that relies on light. This multi-messenger approach, combining precision photometry, high-resolution spectroscopy, direct imaging, and gravitational wave astronomy, is what will truly shatter the current ceiling of our knowledge. It's no longer a question of if we will find systems more complex than sextuples, but when. The dynamic capture theory suggests that under the right conditions, even more elaborate hierarchies could form, perhaps a system of 7 or 8 stars, or a configuration where a sextuple system itself is orbited by another binary, creating an astounding octuple arrangement. These would be the ultimate gravitational tightrope walkers, systems so complex and fragile that their very existence would force a fundamental rewrite of our understanding of orbital dynamics and stellar formation, proving that the universe's ingenuity knows no